Okay, so I'm going to give this voiceover on this lecture on water balance, which is effectively the renal system. So really, you always have to look at the learning outcomes so you know effectively what the purpose of this lecture is, and you know also to know what would it actually ask you to learn, and in effect what's going to be examinable. So overall, what's the purpose of the renal system? A little bit on the anatomy of the renal system. This is a key part here, the processes involved in formation of urine, which include filtration, secretion and absorption. That's a key part. What happens in each part of the nephron, that's another key part. And lastly, to know the role of ADH, which is antidiuretic hormone, and aldosterone. So what's the purpose of the renal system? It's to generate urine for the elimination of waste, especially those nitrogen-containing waste, which is urea and uric acid. Also to regulate blood volume and blood pressure. It does this through adjusting the amount of water that is lost in urine. So urine can have more salt or less salt based on the volume of water within the urine. Also to regulate the plasma ion concentration also by regulating the quantities or the amount of ions lost in urine, principally sodium and potassium, and also regulation of blood pH by controlling the loss of hydrogen ions and bicarbonate ions as well within the urine. So there's a whole host of quite complex physiological controls that are regulated by the renal system. Okay, so this slide here shows us the amount of water intake and water output. The actual numbers, don't worry about these numbers, we're never going to ask you about these numbers. It's just to show you that there's a balance between what our input and our output. So approximately we take about 1.3 litres of water, of this liquid water in various forms. It can be just tap water or just water from anything else you're drinking. There's almost the same amount of in food, because food is not dehydrated. And we've got metabolically produced water, which is really the result of the breakdown of fats. And you can see the total here. For the output, insensible means that what we're unaware of, so really through the skin and through respiration, we lose actually quite a lot that way. So about 800 mils lost that way. We lose quite, not depending on how warm it is, of course. It might be lose by sweat. In this case, it's 50 mils. We lose quite a lot in our feces, but you can see the vast majority of our water loss is actually through our urine. So the output, this urine output, that can be adjusted to account for the amount of water we lose in these other parts as well. So the kidneys actually are involved in reabsorption of various elements in the extracellular fluid, and it's through this thing called tubular reabsorption. And you can see that in terms of substances filtered, the percentage of filtered substances and what is reabsorbed and what is excreted, you can see that about 99% of the total amount of water is actually reabsorbed, and about 99.5% of our sodium is reabsorbed, and all of the glucose is reabsorbed in people who have normal kidney function, and also normal kind of salt balance and glucose balance as well. You can see that in terms of urea, we actually only reabsorb about 50% of the total, and that's because in fact urea is actually used in the kidney to help generate a bigger osmotic gradient. And I've just put in this compounds. These are just kind of or compounds we find in the environment, for example. So like phenol is something that's found in the environment. So that's not reabsorbed, and about all of it is actually excreted. So here's the overview of the renal system. So it looks quite complicated, and the anatomy is reasonably complicated, but it shouldn't be insurmountable. What we have here, the two kidneys, either side of the renal vein and the renal artery, and what we have here is that we have on top of the kidneys, we've got the adrenal glands, just in case you didn't know where they were. And you can see when you cut the kidney in half, there's actually a kind of anatomical features that are exposed to reflect the kind of molecular arrangement of the kidney. So we've got the outer part is called the cortex, and the inner part is called the medulla, and the whole of the kidney is actually surrounded by a capsule called the calyx. And there are these kind of triangular structures here, they're called Marpigion's pyramids, and in here, just at this kind of collecting part of where the urine is actually collected, that's called the renal pelvis, and the urine is actually then is collected and shuttled via the ureter into the bladder, and then the bladder itself, the bladder's output is actually regulated by a number of sphincters, which you don't have to worry about, which then connects to the urethra for the contents of the bladder to be voided. The thing to note here is that the blood vessels associated with the kidneys is actually really big, quite large diameters, and that's for an important purpose. So here's a little bit more zoomed in structure of the kidney. And what's strange about the kidney's actually got lots of fat deposits associated with it, and that's because the kidney has the ability to generate its own glucose, and probably because the kidney is using lots and lots of ATP to generate a lot of the biological processes, so it needs a ready supply of the carbohydrates or fat in order to generate ATP. Now, in this here, we've got an E-4, which is like the kind of, not almost like the repeating unit of the kidney, where all the functions of the kidney occur, and you can see, you see here that if you look carefully at it, you'll see that there's the collecting duct, and we have this kind of round structure. Then we have these kind of convoluted areas here. Then we have this loop. If you remember all those, you'll see so where there's a high density of structures, you see that the kind of high density of kind of material on the actual renal cortex, and the renal medulla, which is looks a little bit more empty. And the reason it's more empty is because we don't have a lot of structures associated with that part of it. So in some respects, you could say that the molecular arrangement of the kidney reflects its microscopic look as well. Now, so we're talking about the blood supply to the kidneys. So they receive an arterial blood supply from the renal artery, and so you can see that in one day, your kidneys actually receive about between 1 and 2,000 litres of blood per day. So it's a huge amount of blood actually going to the kidney. So 20% or so, I think, of the cardiac output actually just goes directly to the kidneys. And the two distinct regions of the kidney, the medulla and the cortex, as I said before, both those regions are involved in urine production. And as I said a bit earlier on, the urine drains into the renal pelvis, and then into the ureter, into the urinary bladder, into the urethra for excretion. And approximately 180 litres are filtered per day, but only about 1.5 litres of urine is actually produced. So the vast majority of the filtration of the kidney is actually reabsorbed. And like I said, the functional unit of the kidney, this is called the nephron. Now this is a complicated diagram in terms of actually the structure of the nephron, and it's because this contains the blood supply as well as the various tubular elements of the nephron. And most textbooks, they tend to strip away the capillaries associated with the nephron just to make it a little easier to see. And they also do another trick in that they straighten everything out. So anatomically, it's actually not a very good representation of the whole thing. And they've done that trick here as well, because I don't know why they bother doing it, because it makes it much harder to actually follow when they do all these tricks to try to clarify things. So the important thing is, so we've got blood coming in this afferent arterial. So it begins with A, so that's always the beginning. So blood coming in, and then it goes into this capillary bed called the glomerulus, and then the glomerulus is actually the blood supply from the glomerulus goes into the efferent arteriole. So we have a capillary bed in here, and then this efferent arteriole then goes along, and we have another capillary bed which is shown in kind of reddy colour, and then we have that capillary bed feeds into the veins, into venules, and then we have the renal vein carrying blood away from the kidney. So in fact, there's two capillary beds. So actually, it's a bit like a portal system. In this case, we're not losing. In this case here, as you can see, because of the colour change, there's actually an exchange of oxygen across because these are actively transpiring cells in the tubular elements. So we're losing oxygen, but we're not losing any oxygen here. All we're doing here is we're actually losing water-soluble elements from the blood, from the extracellular fluid. So the names of these structures are, this is called the peritubular capillaries, and we have so this is the glomerulus, and then the glomerulus then feeds into this convoluted structure called the proximal convoluted tubule. So it's convoluted to actually give us a nice big surface area to help promote absorption and reabsorption. And then it then goes into this kind of loop structure here, which is called the loop of Henle. And the downward one is called descending, and the upper one is called the ascending, sometimes called the thin and thick loops of Henle. And then we end up with a structure called the distal convoluted tubule. So again, a nice large surface area before it ends up in the collecting duct. So we have the filtrate going in this direction, and then we have the blood going in the opposite direction. So we actually have this thing called a counter current system set up, and I'll hopefully explain that to you in the next slides or so. Now, this is basically just the process by which the nephron deals with filtering out substances. So again, we have the afferent arteriole, so blood going into this glomerular capillaries, and usually though it's not drawn very well here, and it's typical of all these diagrams, this afferent arteriole should have a nice large diameter. This efferent arteriole should have actually a quite small, relatively small diameter. This afferent arteriole should be quite short. This efferent arteriole actually should be quite long. So what that results in is that blood flows in here quite readily. It you get an increase in blood pressure within the glomerular capillary bed because the blood can't flow out particularly well. So that acts that pushes substances out the glomerular capillaries. That's why that one is the filtration portion of it. So you could actually think about this structure here a little bit like a biological filter paper. So it pushes water-soluble substances out, low molecular weight substances, no blood products at all, just salt and glucose and amino acids and all the low molecular weight and water-soluble substances. It gets collected into this structure called a Bowman's capsule, and then as a consequence of losing stuff, so we've lost ions and various elements within here, so the afferent arterial supply has actually got a lower concentration of it, and that then means that there's an opportunity for things to be reabsorbed as required. So we get reabsorption by the peritubular capillaries, and sometimes you get things actually being secreted by the peritubular capillaries as well. So this is an active. Remember, this is an active process going all the time. And then what is not reabsorbed and what's not secreted and what is secreted, it eventually ends up as the urinary product. So this is another kind of complex looking diagram of the various elements of the nephron, and so it's showing you that here in red we've got active transport, and in grey we've got passive transport. So things that move passively are actually just using the concentration gradient or the osmotic gradient to move substances. So when you see water moving, water can really only move from a low salt concentration into a high salt concentration, so high water to low water effectively. Whereas when you see active transport in red, that must mean that ATP is being expended and actually move that substance actually against its concentration gradient. Otherwise, if there was ions there, ion channels there, the substances would just move by passive diffusion. So the arrows show you the movement of substances, and the various areas actually show us what's been moved around the place. Let's look at the glomerulus. So blood is filtered into the renal tubule from the glomerulus to form the filtrate. So the afferent arteriole, like I said, in the capillary bed here, pushing things into the Bowman's capsule. So the filtrate has the same composition of plasma, and it's the high blood pressure in the glomerulus itself, in its capillary bed here, that forces fluid into the renal tubules. And the glomerulus and a Bowman's capsule, which is this whole thing here, sometimes collectively referred to as the renal corpuscle. I wouldn't worry too much about that. So let's look at the proximal convoluted tubule. So really, I'm just wanting you to have an appreciation that substances are transported, recaptured by both the proximal and convoluted tubule. Actually, the proximal convoluted tubule probably does most of the work. So it's really it's getting rid of these breakdown products of proteins, ammonia, and get rid of some hydrogen ions as well. It's also involved in because it can regulate the amount of hydrogen being moved around. It can therefore regulate the blood pH. But the important thing is that it's involved in the reabsorption of glucose, sodium chloride, water, potassium salts, and this bicarbonate ion. So the things that are effectively lost as a consequence of filtration are then reabsorbed at this point here. Don't forget, there's a capillary network, the peritubular capillaries, that are helping to keep these concentrations low to ensure that things actually that require a concentration gradient, that concentration gradient is actually maintained. So loop of Henle. So loop of Henle is an unusual structure. It passes between the outer medulla and the inner medulla. The descending loop of Henle is freely permeable to water. So permeable to water, but not to descending. Permeable to water, but not to salt. So water can move out of the descending loop of Henle. It can only do that if there's an osmotic gradient to facilitate its movement. And in most cases, as you'll see later on, there is a huge osmotic gradient running the length of the loop of Henle in order to facilitate the movement of water. So it's a passive movement of water in the descending one. And the water that moves into the extracellular fluid effectively, or extracellular space, is reabsorbed by osmosis. So therefore the interstitial fluid must be hypertonic to the filtrate to allow the water to move. That's just really saying is that the water is moving by osmosis, and that water is then recaptured by the peritubular capillaries, so that the concentration gradients associated with water being pulled out of the descending loop of Henle is maintained. Now look at the ascending one. So the interesting thing, to me anyway, is that it's only permeable to salt but not to water. So sometimes it's called the thick or the thin thick, the thicker thin elements of the ascending loop of Henle. So reflecting that there's an increase in the differentiation of different types of cells, in fact, and these cells require to be metabolically very active in order to move these salts against their concentration gradients. So permeable to salt but not to water, and we get the passive reabsorption in the thin segment of the ascending limb and active reabsorption in the thick segment. So the active part is demonstrate that the slightly different cell type associated with the movement of salt out of the ascending limb. And this passive movement is simply due to the salt gradient. Now, here we have this thing called this countercurrent multiplier. This is probably the most complex of any of the slides that you'll ever see, and mostly because there's large numbers, it makes it actually quite a challenge to get your head around. And what I usually always do is I get people to look at the numbers first of all, and I just want to look at the trend in the numbers. So if you look at the descending loop of Henle and then the ascending, so that's the distal corner of the tubule to the proximal corner of the tubule has been cut off. And then we have the collecting duct. And what you'll see is that as the osmotic pressure, which is these numbers here in milliosmoles, the osmotic pressure in the filtrate increases. So it increases simply because we're actually losing water into the interstitial fluid between these two tubules. Because we're losing water, the salt concentration in a descending limb increases, and therefore the osmotic strength of the filtrate increases, and it gets to approximately 1400 milliosmoles. And this is where the urea comes in to help. The urea really helps to increase the osmotic strength of the bottom end of the loop of Henle. And then as you see, as the filtrate goes up the loop of Henle, you'll see that the numbers start to get smaller. And the reason the numbers are getting smaller is simply because we are losing sodium chloride. So sodium is actively pumped out of that part of it. And therefore, as we lose sodium, we effectively, it's equivalent of gaining water, and the osmotic strength actually starts to fall quite considerably as we go up to the distal convoluted tubule. And as we go down the collecting duct, you can see the osmotic strength starts to increase. And the osmotic strength starts to increase because we're actually getting diffusion of water out of the medullary collecting duct in order to scavenge water. So in my mind, the whole purpose of this part of the kidney is actually to regulate how much of water is in the final part of the urine. So if you need more water, you need to reabsorb more water, you can actually then regulate how much water actually is moving across the walls of the collecting ducts. And if you make this more permeable to water, then water will move into the interstitial fluid, following the osmotic gradient. So all along here, there's osmotic gradient which is actually promoting the reabsorption of water. So here we are here. The descending loop of Henle is relatively impermeable to solutes and freely permeable to water. The ascending limb is permeable to solutes, but not to water. Solutes, sodium. Urea recycling contributes to the medullary osmotic gradient to try to push the osmotic pressure up as high as it can. Water moves through aquaporin channels, so the aquaporin channels here and in other parts of the tubular structures. So don't forget that it's not drawn like a cell, but these are all individual cells. They've all got plasma membranes, so therefore they've all got phospholipid bilayer. Water and fats don't mix, so the only way that water can get across is actually through a water-filled channel of some sort. So there are these things called aquaporins, so they're water channels, and these aquaporins vary throughout the tubular segments, and they're highly expressed in the proximal nephron. And there are a whole family of them. Don't worry too much about the whole family of them, but it's just that they can be the numbers can be regulated by this hormone called antidiuretic hormone, and especially in the collecting duct. So in the collecting duct can be the permeability to water can be acutely regulated by antidiuretic hormone. Okay, let's look at distal convoluted tubule. Now the thing about the distal convoluted tubule is that it's in this diagram and the previous diagrams, the whole nephron's been stretched straight out, so it's like a linear structure. But in fact, the distal convoluted tubule actually bends back in itself and it interacts with the afferent part of the blood supply going into the kidney, and I'll tell you why that's important later on. So what we have is more secretion of hydrogen and potassium, regulation of potassium concentration and the blood pH. So some diuretics work in the distal convoluted tubule, and the reabsorption of hydrogen bicarbonate, and which is sometimes dependent on the pH, and further reabsorption of salt and water. So the distal convoluted tubule acts to kind of tighter the levels of these different substances, but note that we're not getting there's no glucose being reabsorbed here, because all the glucose hopefully has been reabsorbed in the proximal convoluted tubule. So proximal, closest to the nephron. So let's go on and look at this distal convoluted tubule, where it is correctly anatomically positioned. So here's the distal convoluted tubule, just here, and here we have the glomerulus, the capillary bed. Here's the afferent arteriole. Here's the efferent arteriole. This time the drawing is actually a little bit better. This diameter here is quite large. This diameter here is quite small, and the length of this is actually quite long. So we actually have a pressure difference across here. High pressure coming in here, and we've got and the pressure actually drives the water soluble substances across the glomerulus, across actually across a cell type called a podocyte, which you don't really have to worry too much about. But the podocyte is almost like biological filter paper, so it helps to exclude large molecular weight compounds and blood cells, etc. If I remember rightly, I think they're negatively charged to help repel positively charged proteins, so they don't get all bunged up. We've got these things called mesangial cells, these mesangial cells, and they're kind of strange cells because they can actually contract and help to regulate the amount of blood flowing into the capillary beds, in fact. So we've got a sympathetic nerve fibre, I've got this thing called the juxtaglomerular cells, and we've got the distal convoluted tubule, but we've also got a specialist cells in the distal convoluted tubule called the macula densa. So the whole thing is called the juxtaglomerular apparatus. So the distal tubule contacts the afferent arteriole at the renal corpuscle. So the nephron comes back in itself, and the distal part comes back in itself and interacts with the arterial supply going into the glomerulus. And the juxtaglomerular cells, they're modified smooth muscle cells in the afferent arterial wall. And the important thing is these juxtaglomerular cells, these cells here, they can detect changes in blood pressure, i.e. they can detect if there's too high blood pressure or too low blood pressure. Usually they're looking for too low a blood pressure, because if the blood pressure is low, if the blood flowing in is low, then you're not getting good filtration, and then the kidneys have a mechanism in order to try to maintain blood flow into the kidney to ensure that we get good filtration of the plasma. And in order to do that, they secrete an enzyme called renin, and that renin triggers this thing called the renin-angiotensin renin-angiotensin system if the blood pressure falls, to try to maintain the filtration of the kidney. So here we have the renin-angiotensin system. Like I said, the distal tubule contacts the afferent arteriole at the renal corpus. And we've got these macula densa cells. So they're in the distal tubule, and they monitor this multi potential in the filtrate in the distal tubule. What that really means is that they're monitoring the amount of sodium in the filtrate. And if there's not enough sodium, that means then potentially there's actually the filtration rate is actually low. Then these juxtaglomerular cells then stimulate or the macula densa cells then stimulate the juxtaglomerular cells to release renin, because that's a kind of indicating there's insufficient filtration or low blood volume, low blood pressure. So both the juxtaglomerular cells and the macula densa cells, they work together to regulate blood pressure and blood volume. So let's look a little bit more about the renin-angiotensin system. So like a lot of biology, many of these organs, they don't really work in isolation. They work in conjunction with other organs, either directly or indirectly. And in fact, the kidneys actually work in conjunction with the liver. The liver hepatocytes, because the liver hepatocytes, they secrete an inactive protein, an active precursor protein called angiotensinogen, and that's in the bloodstream all the time. And as I said before, the juxtaglomerular cells, they secrete the enzyme renin, and that renin then acts on the angiotensinogen to generate angiotensin 1, and that angiotensin 1 is the concentration of angiotensin 1 increases in the bloodstream. Now, the interesting thing about angiotensin 1 is that because it's in the blood, it is then transported to the lungs and to other tissues as well, where there's a membrane bound protein called angiotensin converting enzyme called ACE, and that converts angiotensin 1 into angiotensin 2. Now, the point of this is that although both angiotensin 1 and angiotensin 2, they both promote an increase in blood pressure and blood volume. So they cause vasoconstriction, and they also promote or facilitate the reabsorption of water. So that ACE is interesting everyone just now, because this enzyme, this protein in the epithelial cells of the lungs, that looks like that might be a target for this coronavirus that's kicking around, and maybe a few other viruses. So the virus actually has got a binds to angiotensin converting enzyme, and that's how it manages to get into these cells and to replicate. And as a consequence of the way the viral proteins replicate, they unfortunately then, in order for them to be redistributed, they cause the cell to lyse, and that lysis actually then destroys an important epithelial layer in the lungs, which actually promotes inflammation, and lung function is drastically impaired. So the thing about the renin-angiotensin system is that if we get a decrease in blood pressure, BP blood pressure, or blood volume, it causes the release of renin from the juxtaglomerular cells, which converts angiotensinogen into angiotensin 1, and the ACE converts angiotensin 1 into angiotensin 2. And like I said, that causes peripheral vasoconstriction, so stops blood in those areas of the body that are not really required, to the skin, maybe to the gastrointestinal system, and that causes that diversion of blood then increases the blood pressure. The thing is, the efferent arteriole, so that's the arteriole that is leaving the glomerulus, that constricts, and if that constricts, that increases the pressure within that little capillary bed within the glomerulus, and that helps to maintain glomerular filtration rate, GFR, glomerular filtration rate. And the angiotensin 2 acts on the posterior pituitary to release antidiuretic hormone, and the adrenal glands also secrete aldosterone. Excuse me, I've got epinephrine is E, and norepinephrine is NE. Because that's a kind of American term. Epinephrine is adrenaline, and norepinephrine is noradrenaline. So both effectively hormones to drive up blood pressure. So the result is an increase in blood pressure and blood volume, because antidiuretic hormone actually increases the permeability of the collecting duct, which actually more water is reabsorbed. Aldosterone is secreted, and that actually then promotes the reabsorption of salt as well. So both of them to try to raise blood pressure and blood volume. Let's look at the collecting duct. So it's permeable to water, but not to salt. We get some passive reabsorption of water, and the far end of the collecting duct becomes permeable to urea, where some of it is reabsorbed. So it helps to maintain the concentration gradient so that water can be reabsorbed. That's the urea I'm referring to. Helps to maintain a concentration gradient so that water can be reabsorbed. So really this is the main part by which water is reabsorbed, and therefore having a osmotic gradient going from 60 to 1,200 gives you a great opportunity to actually to tighter the amount of water that is being reabsorbed. So the key renal hormones, what are they? We've got antidiuretic hormone, and that's released from the hypothalamic pituitary axis. It's released when blood osmolarity is high, and there's a high concentration of solutes. It activates the nephron collecting ducts to become more permeable to water, and therefore you get an increase in water retention. And just a wee note for ourselves, so alcohol is quite a potent inhibitor of antidiuretic hormone, and that's why if you drink alcohol, you get an increase in frequency actually go to the bathroom. So your urine's a little bit more dilute, and alcohol actually acts as a dehydrating agent as a consequence. So renin-angiotensin-aldosterone system. So low arterial blood pressure results in renin secretion, which converts, as I said this before, angiotensinogen to angiotensin II. This causes arterial constriction and increase in sodium chloride and water retention in the proximal tubules, and it also stimulates adrenal hormone aldosterone, which causes increase in sodium and water reabsorption in the distal tubule, all to promote to kind of facilitate raising blood either by volume or osmotically. So almost at the end here. So the purpose of the renal system, so to generate urine for the elimination of waste, like I said before, especially nitrogen-containing waste, regulation of blood volume and blood pressure, like I said to you earlier on, by adjusting volume of water loss in urine, and there's a number of mechanisms by which that occurs. Regulation of plasma ion concentrations by regulating the quantities of ions lost in the urine, and also the regulation of blood pH. We haven't really mentioned how blood pH is regulated. There's not enough time in a lecture to do that, but just so you're aware that one of the important roles of the kidney is also to regulate blood pH. So what we'll try to do today is that you've got a good idea of the structure of the nephron. You've got a good idea of what happens in each part of the nephron, especially the glomerulus, the proximal convoluted tubule, the loops of Henle, and the distal convoluted tubule, and the collecting ducts, because they're all doing something slightly different, and the role of a number of hormones in actually regulating the permeability for water and also to promote the reabsorption of salt.